So we're here today to talk to you about optimizing mobile applications. But first, just to introduce ourselves, I'm Mark. That's a really old photo, but everything else involves me with my hair down at metal shows, so it never looks like me. I'm a developer relations engineer at Unity. I've been at Unity for almost 6 years now, hard to believe. Currently, I'm based in North America, where I travel to our customers, help them with performance problems, help them to unblock them on critical issues. And from that, we're currently generating best practice documents, which kind of, from the hotspots we've identified, these are core areas that people sometimes have problems with in Unity.
Hello, my name is Ian. I'm also a developer relations engineer at Unity. I've been doing this for 3.5 years now, and whereas Mark handles the Wild West of America, I am based here in Europe. So, Mark.
Okay, so what we're going to cover in this talk is optimizing Unity projects for mobile applications. What we want to do is give you an insight into the tools that are available, such as Unity's Profiler, but also the native tools for the platforms, such as Xcode instruments for iOS. And though we've aimed this talk directly at mobile, most of what we're talking about is valid techniques for other platforms. Now, the main points that we want to get across are, how do you get good data? This means, how do you gather the information you need to be able to identify the causes of any problems? Eliminating the guesswork is key to this, and basically what we're trying to do is help you optimize the process of optimization. It will cover the most common problems we found in our travels, along for memory and CPU usage, and provide solutions to those problems. But now Ian's going to talk for a while.
Right, because before we actually start talking about optimization, we have to discuss profiling. Any attempt to optimize a game blindly is likely to fail. So the first thing you should do when you have a game that you want to make run faster is get good data. Find out what is slow. Start there. To do that, you need to use good tools. The tools in this slide here, these are the ones that you probably want to start with. So we've got Xcode's instruments, we have the Snapdragon Profiler, we've got vTune. The Unity editor, of course, is an excellent place to start. It's built in. It's very good for comparative profiling, trying to analyze which different parts of your application are more expensive or less expensive. It's also great for looking at how you're abusing the garbage collector. In 5.3, there's a bunch of new tools, and Mark is going to talk about those in a little bit. But, as many of you may know, anyone who's tried to optimize a Unity game with just the Unity Profiler knows the Unity Profiler is limited. There are places in the engine that it cannot profile. We've all seen that overhead bar in the CPU profiler and wondered what's going on in there. Fortunately, on native platforms, on things like iOS and Android, we can use these native tools, and the best of them is Instruments. It's free. It comes with Xcode, and I encourage everyone here to use it if you haven't already. And because Unity produces native code, C++ now, thanks to IL to CPP, Instruments can provide millisecond method-level resolution profiling data for your game. Better yet, it can see into things that the Unity Profiler can't see, such as application startup time. If you haven't used Instruments before, we actually posted a blog on this a few months back. The link is on this slide, so when this talk is on YouTube, I guess you can get it from there, take a photo. We'll try to get the slides to you somehow. I encourage you to try it out. When you do open Instruments, this is a screenshot from the time profiler. What you have here is a call tree that lists all of the CPU time that is being used while running your application. This is both actually Unity's internal code as well as your transpiled scripts. So if you want to see how Unity runs internally, I encourage you to just spend a little time playing around, looking through the call tree, and you can discover a lot about how Unity is architected. There's two places where Instruments can provide some really interesting insights, though. On this slide, I've highlighted in red the start Unity method. As you can probably guess, this is the code that runs when Unity is first initializing. This is actually running while the splash screen is open, so your application is not yet interactive. And while most of this is actually Unity's internal system starting up, there are two ways that your project can affect the performance of this part of the code. First, you'll see in the middle of this slide, if you're sitting up close or if you're zooming in on YouTube, player load global managers. What this is doing is is initializing many of Unity's internal singletons and registries. One of the ones inside of here where your code can affect it is the resource manager. This object governs the resources system. If you've got any files in your resources folder, the cost of loading the index of those files will show up in this method. The second place where your code can actually affect the performance of the splash screen is further down. It's inside the player load, the awake function. Further down, you'll actually find the Unity load scene method, which actually loads and awakes the first scene in your game. This is actually done before the splash screen is dropped. So if you have any expensive code inside an awake method and a mono behavior that is attached to a game object in your first scene, you may actually be slowing down your launch. Perhaps consider moving that later in the application's lifecycle. Instruments also provides excellent data for when your game is running. Now, this is aggregate data. Unlike the Unity profiler, you can actually select and view data that runs across multiple frames, or actually you can dissect a single frame. On this slide, I've highlighted the PlayerLoop function. Again, as you can guess, this is Unity's main loop. The code inside of this is running once per frame. There's a lot of stuff that goes on inside of here, so I'm going to highlight some of the most interesting ones. First, since we're playing video games, most of your game should be running video, and so the player render function should hopefully be at the top of your call stack. This is actually running Unity's render loop. So this is running your culling, this is running dynamic batching, this is uploading VBOs to the GPU, and so on, setting the passes on your shaders. If you have any rendering-based script callbacks, any image effects, on-will-render object callback, the on-pre-cull callback, all of those will show up inside of here. Next, and probably the most interesting, there will be 3 functions called on the base behavior manager object. In fact, the common update function is templated, so if you see it templated with update manager, that's where your update loops are going to get called. If you see it templated with fixed update manager, your fixed update loops, late update manager, as you can guess by now, your late update loops. If you're trying to address the performance of your scripts, that's where you should start. Other things that you can see in here, if you're using Unity's UI system or any other UI system that uses Unity's canvases, you may see some computation in the UI canvas manager. This system calls each canvas in your scene at least once per frame, and it tells that the canvas is going to be rendered. So this is where Unity UI does its text layout. It recalculates layouts, calculates text sizes, creates VBOs for your text, and then actually does all the batching computations. So if you've got something expensive going on in there, you'll see it inside the canvas manager. You may also see the delayed call manager. If you have any long-running operations, things that run across multiple frames, like coroutines, that'll show up in the delayed call manager. Coroutines are actually fairly complicated, so I'm going to go over those more in a little bit. There will also be a call to the physics manager. In fact, it's going to be called physics manager fixed update. This is actually running physx itself. It's ticking the physics scene. So if you go down inside of there, what you'll mostly see is the guts of physx. In fact, what you'll probably mostly see is a lot of calls to the job queue, which is Unity's internal multi-threading system. However, if you have any physics callbacks, such as on collision enter or on trigger stay, those are likely going to show up in here. If you're using any 2D physics, you'll see physics 2D manager as well. There's a lot of other subsystems inside of Unity, but let's look at profiling your scripts. So here's a screenshot from the time profiler once again. This is actually from the sample assets project, one of the scenes in the sample assets project. What you can see here is in the call tree, you'll see a scripting invocation object. Anytime Unity is calling C# scripts, it goes through this object. Below there, there'll be the runtime invoker, and that's the last point inside of Unity's own code. After that, it's all your C# scripts transpiled. So what we can see here is actually the event system underscore update method. That's the event system class update method. That is actually the most expensive thing in this scene by about 100 times. So if I was actually going to go in and optimize this application, I'd unroll that line and see exactly where all the CPU time is going. In this case, actually, we're running on an iPad, and what we're doing is we're running the standalone input manager, and we're looking for the mouse every frame and raycasting into the scene to find what the mouse is over. Now, I don't know about you, but I don't have a mouse attached to my iPad, so this is pretty silly. If we disable that, that entire chunk of time disappears. Now, Earlier, I mentioned coroutines. I said they were a little strange. Let's take a look at profiling a coroutine. Here, once again, we see the scripting invocation object, and below that, the people sitting in the front row probably see a very strange method name, u3c do bob cycle. Do bob cycle is actually the name of the coroutine itself. What this does is simply shakes the camera around while it's following our object of interest through the scene. Now, since this coroutine runs for many frames, it's adjusting the camera's position every frame, most of the cost of this method will show up here in the delayed call manager, but not all of it. And in order to explain why not all of it is going to show up here, we actually have to talk about how coroutines work. You see, coroutines are actually supported by an object. This object is actually generated by C#. You don't have to do anything to create it. The object tracks the state of the coroutine. It tracks where Unity needs to resume the execution of the coroutine when it's going to begin executing it again. Because of this, the cost of the coroutine will be split into two places. First, Unity runs all of the cost of the whole coroutine from the start of the coroutine down to the first yield exactly when you start the coroutine. So that you'll see a start coroutine method in your call tree, then a bunch of code. Finally, when it yields and it resumes again, from the first time it yields till the coroutine finally terminates, that will actually all show up in the delayed call manager. Finally, instruments can also be used to identify places where Unity is loading assets. If you see a method called virtual redirect transfer, that is Unity's serialization system transferring data into some object. Usually, this happens when you're loading an asset. It could be a texture, could be a mono behavior. In this screenshot, it's actually a particle system. So if your game's performance stutters and you see a lot of time going to virtual redirect transfer, you may need to preload some assets, pool something, or perhaps you want to make your asset loading asynchronous. You can also find this method deep inside calls to clone object. In that case, it's, of course, transferring the data from the source object to the target object. I think Mark wants to talk about memory, though, so I'll pass it over to him.
You can keep hold of that.
I can keep a hold of this.
Yeah. You know the bit that you need to do with the animations, it's fine. OK, so now I want to talk more about memory and the problems that I've came across with memory in a lot of games, how to resolve them, common causes, etc. So who here is using Unity 5.3? Cool. OK, so how many of you have seen this tool? OK, that's not enough people. So this tool is the memory profiler that was added in 5.3. It allows you to get the entire contents of memory, all your native allocations, and all the allocations in the managed heap. The tool, its main power is that it gives you a way to track the references from a variable in your script back to the object, to what's holding onto it in memory. So if you're having memory problems, you can open up this snapshot, click on something, and then it will give you a reference chain back to the variable holding onto something. It's a great way for tracking down memory problems. Further to that, though, the tool is actually built on a public API. So you can modify it in any way you want to do things you want. So you could take one snapshot, take another one, diff the two snapshots, and see what's actually growing in memory over time. It's a great way for tracking down all your memory tools. The only drawback is that it only works on IL to CPP platforms. But this is a talk about mobile, and mobile is available for iOS, and IL to CPP is available on Android as well. So it's great. The tool's hosted on our Bitbucket, and this is probably why some of you haven't came across it yet. I would highly recommend visiting our Bitbucket. There are tons of cool projects on there, little snippets and things that you may not know Unity is actually capable of doing. It's an invaluable resource for most of our users now. Now, the project, it comes as a complete Unity project, but it's just an editor folder full of scripts, so you can just drag and drop the editor folder in. Once it's finished compiling, just run a development build of your application, connect the profiler. We need the profiler connection open. Then if you go to Window, Memory, it opens the window you see, or you would see in the previous slide. Then you can press Take Snapshot. And at this point, you have to have some patience. It will freeze your game on device for maybe a second. This is us gathering up everything in memory. Then we send it over the connection. Your game unfreezes. At this point, you can click on your editor. If you're on Mac, watch it beach ball. If you're on Windows, watch it go to not responding, because I've seen this take anywhere up to 30 minutes to parse everything that's in memory. You have to be patient. But once you've got that snapshot, you can save it. Everything's much easier. So, common use cases for this tool. If you're on mobile, show of hands, who's using asset bundles? Yeah. So I'm sure some of you have hit the common problem where you have an asset bundle, you load it, you load your texture, you do asset bundle unload false. You can then load that same asset bundle and the same texture again. The reason for this is when you do asset bundle unload false, internally in the engine, Unity has no way of knowing that that first texture is actually loaded. It doesn't exist in our persistent manager anyway. So with this tool, you can quickly look at two textures, go, they're the same size. And then when you look at them, actually you might be able to read that. You can see the textures would have the same name, but just a different instance ID. So you know you've run into this problem. It then gives you the reference chain back to the variable that allocated it, so you know where it came from. It's super easy to track that down. And obviously, the common solution to that is just to wrap everything in your own loading manager that holds a reference to everything you've loaded. So you know when something requests something again, you go, oh, this URL, this asset, just give back the reference to the first one. The other useful example here is for image effects and your render textures for your application. Now, an iPad Air 2 at full resolution, the render textures and back buffers are 36 megabytes for full resolution. That's like 4K resolution on a mobile device. Consoles aren't rendering 4K. PCs are very rarely rendering 4K unless you're spending several thousand euros here, I guess, on graphics cards. So think about downsizing your render buffers to something more saying like 1080p. You half that size, it's 60 megabytes, and then your render textures for image effects are kind of like half size, so they're only 8 megabytes. It's actually a really quick way to get a lot of memory back. But now I want to talk about the single most common problem I've came across on the road, and this is the assets in your projects themselves. And what I want to discuss is auditing your assets in your project. What I mean by that is just developing an automated system for controlling the import settings on your project. By controlling these settings, the intention is that all the assets in your project will have the correct import settings applied to them. So the reason why we suggest this as a best practice is to prevent mistakes. The people on your project are human. As such, they're prone to making mistakes. So automating this, hopefully we can remove the human element. So the classic example of this, and the reason why this came up initially, was people using the NGUI GUI system. It generates 4K uncompressed textures by default for your GUI atlases. Now, on iOS, that's a 60 megabyte texture, 60 megabyte allocation. So on an iPhone 4S, that's actually a third of about the safe memory you can use. Just by compressing that, brings it down to around 8 megabytes. So that's 52 megabytes of memory back, just by checking a little box. It's really, really easy to fix. However, this tool was not obvious in the past. This mistake was not obvious in the past with the tool set that was available, but the new memory profiler makes this very apparent very quickly. So, common mistakes that I've seen are insane texture sizes, the 4K textures, just throwing memory everywhere. In the scene view in the editor, there is the bitmap viewer. If you go in there, it actually shows you the texture resolution compared to the number of pixels that are being rendered on screen. You can actually quickly see that a texture is too high or too low resolution. Compression, apply it to everything. Artists in the room might argue about that, they might not, but use your best judgment at the level of compression you're applying to your assets. Make sure it's not actually impacting on the quality of your game. When dealing with lots of animations, make sure the rig is correctly set up. There are no free bones being animated that are redundant applied to them. But the main problem here is that every type of asset has a different set of rules that it needs for every different platform. So this quickly balloons into something uncontrollable. So some of you may or may not know about the asset post-processor class. It's a class that receives callbacks. Anytime you import or modify an asset in your project. This way you can intercept what's going on before Unity changes anything. Now, the most important ones to implement are the on-pre-process methods. So on-pre-process model, on-pre-process animation, on-pre-process audio, on-pre-process animation. So you grab this before anything happens, and then you can make the changes you need. So a simple example here, and this example is actually really important, and I'll explain why later on. You get your read-only model processor class that inherits from asset post-processor. Override the on-pre-process model function. You get the asset importer variable, which is part of asset post-processor. Cast that to model importer because you're dealing with models. Then we're checking if it is readable. If it is, we set that to false. We save and re-import the model, which then immediately calls this function again, but this time it's set to false, so we don't do anything to it. Now, common rules, just as a quick sidetrack. On textures, make sure read-write enabled is disabled. The reason for this, it stores 2 copies of the texture in memory if this is enabled. So you're doubling your texture memory straight away by this. So make sure it's off unless you're actually doing pixel operations on your textures. Disable bitmaps is really useful. Anything that's not changing in Z depth relative to the camera, disable it immediately. So this is your UI, any 2D assets, just disable it across the board. For 3D, it will be more expensive on the GPU because you're not getting the lower bitmaps, so it's eating up sampler bandwidth on the GPU. But if you're not GPU bound, then you can get away with doing this, and it will save 1/3 of your texture memory. Then, compression textures. It will save huge amounts of memory. Anything uncompressed will just be blowing out your memory in ways that are not generally very nice. Now, models, again, make sure read-write enabled is disabled. This is on by default on every mesh you import. So if you've not changed this in your project, you can go away, turn this off, and save half of your mesh memory on mobile. The only caveat to this is it needs to be on if you're using mesh colliders. PhysX needs that ability for generating the mesh colliders at runtime. So if everything isn't changing and you're not using mesh colliders, go away, do that, and save a bunch of memory. Disable the rig on non-model character models. This prevents an animator being instantiated at runtime, and this stops just an extra tick going into our animation system. Then mesh compression. Generally, on mobile, setting it to low, I've never really noticed any difference. Medium, depending on the quality of the model, you might start to see something. But the difference with mesh compression compared to textures is that in the player settings, you can pick which channels you actually want to compress. So you can compress everything apart from the vertex data. So it won't alter the spatial dimensions of the vertices, but you can reduce the quality of the normals and tangents, which is probably OK. Now, just a side note to this, because it didn't fit anywhere else into the talk. If you instantiate models at runtime and you're constructing objects from code with mesh renderers, by default, casting shadows is on, receiving shadows is on, light probes is on, reflection probes is on, and in Unity 5.4, motion vectors will also be on. So turn these off. If you're not doing shadows, just having one random object will initiate the whole depth shadow pass on the GPU in Unity. So it starts eating into your GPU time. So just a quick side note. Audio, believe it or not, bring in the highest quality raw files you possibly can into your project. We compress them at build time for device. So there's no need to import MP3s. You can get your nice, high quality WAV files in there. Then for iOS, use MP3 exclusively. It's supported by the hardware. It's faster and generally better. Then Vorbis for Android is similar there. Now, for mobile games, force mono. I mean, how many people, sorry to all the audio programmers, but how many people actually listen to the audio on their mobile games? Most people on the train are listening to music whilst they're playing. So don't place too much emphasis on this if you're needing to save some memory, and then set bit rates lower as well. Now, I don't want to be patronizing, I don't want to be condescending for this next section, but I've had to explain this to senior devs, and I sighed heavily because of this. But one of the main issues users face is the unexpected expansion of the managed heap. And this is particularly problematic because we don't collapse the size of the managed heap at runtime. So the white area represents the entire managed heap, and the colored rectangles within represent allocations in there. Then if we need some memory, we find an empty space, we drop it in there, and everything is fine. Periodically, the garbage collector will run. It scans every object, makes sure there are no references to it, and anything that's unused gets deleted from memory. Now, we will reuse that memory space if something can fit into it, but if we don't, you're just left with unused memory in your project. Depending what you're doing, this could be large, it could be small. Now, what happens when there's not enough memory for new objects? What we have to do is expand the entire heap to fit this in. And this isn't a permanent expansion. So now we have even more unused memory. Now, remember, the heap only expands, it never shrinks. And this is bad on low-end mobile devices like 512 megabyte iOS devices where you have about 180 megabytes of memory for your game to fit into. So how do we avoid this? Temporary allocations are the worst. So 1 kilobyte per frame of managed allocations over 60 frames is 60 kilobytes. Over 1 minute, it's 3.6 megabytes of memory. You're just churning through. And this is not good. Now, consider this. The garbage collector will only run automatically as the managed heap has almost filled up. So say you're at that point where there isn't much space left, and then you do an expensive operation like loading where temporary allocations are generally unavoidable. You're going to expand the managed heap. All those temporary allocations are going to disappear, and then you're going to be left with this huge empty space in memory, maybe 10 megabytes or more, which is like 21K textures on iOS. So it's not good. Now, solve this. Use the Unity profiler, CPU panel, GC alloc column. Everything you find in there, kill it with fire. Hard. Small allocations may look like, it's only a few bytes, but it soon adds up over a long time of gameplay. But bear in mind, if you do this in the editor will show some allocations that don't happen on device. So make sure you're not chasing ghosts in this situation. So, other ways you can serve memory. Reuse your collections, your lists, your dictionaries, etc. Calling clear in these doesn't free the memory, it just gets rid of the contents. So you can reuse this. If you have that script that has lots of methods that have temporary lists and dictionaries in there for doing operations, think about making it a field and then just calling clear on that list at the start of the function. It stops this constant churn in memory. It really, really helps. Avoid strings. Strings are immutable, so every time you change one, you allocate a new string in memory. Use things like string builder to avoid unnecessary allocations for this. Avoid closures. They will take locally scoped variables and allocate them on the heap instead of the stack. And anonymous methods, some of that lovely C# syntactic sugar, will create a temporary object on the managed heap because they cannot be treated as value types. Currently, however, this doesn't actually show up in our profiler, but we've made our scripting team aware of this and they're working to fix that, so hopefully soon. Boxing. Ian's going to talk about this more later because it's one of our pet peeves, but it's a common cause of temporary allocations. And it just happens when you pass a value type as a reference type. So classic example is enums for your key in a dictionary. This is very common. I find it convenient. Everyone finds it convenient. But there are ways to solve this. So firstly, on here, the call to dictionary.add will box the enum object because it calls object.getHashCode object, which takes object as an argument and not an enum. So the enum is therefore boxed. What it also does is create a temporary comparer object to do this comparison. So you get this double allocation, which is kind of horrible. It's really simple to fix. You create your own custom comparer using I-equality comparer and pass that to the dictionaries constructor. Everyone's favorite. Don't use them. They're bad. They're slow. They're half as slow as for loops for a start. So we can have that argument afterward if we need to. You find me outside, I'll put my boxing gloves on, you can find yours. But currently, in Unity's version of Mono, it allocates a temporary enumerator object. It's only small, but when they add up over multiple nested for each loops, it can get really, really bad for your project. So only use them for types where it makes sense. Now, some of Unity's APIs cause GCAllocs as well. These are kind of unavoidable on our part, but it does happen. So what they do is they return an array every time, and it's a new copy of that array. So you just end up with multiple copies being temporarily allocated. And there are other APIs that do this. For example, mathf.max. It can take params. Every time something takes params, it actually converts that to an array to pass it around. So these things happen in places where you might not expect. Now, because we're on mobile here, let's talk about touch. So this code here allocates the array twice per loop. Once for input.touches to get the length, and one for the array access. By doing what is now on the screen, you're only allocating that once before the loop. And then this version, there are 0 allocations at all. So there are versions of the APIs which can solve these problems. But now Ian's going to talk more about CPU and runtime performance.
Absolutely. So thank you, Mark. He's covered a lot of things about memory. Let's move over and talk about CPU performance. I mean, it's great if your game fits in under 180 megs of memory, but if it runs at 3 frames per second, no one is going to want to play it. I'm going to start by talking about loading time, because at least personally, I don't like staring at splash screens. One of the things that we find when we go to customers, a lot of people like to store their game data in JSON or XML. Maybe they're delivering it from a web service, and they need to parse this at startup time. Unfortunately, text parsing, and especially JSON and XML parsing, these are incredibly slow, and many people use parsers based on reflection. Now, reflection is great when you're still developing your app. However, reflection is probably one of the slowest things you can do in C#, short of a few other things that I'm not going to go into. But while reflection lets the parser be very, very flexible, trying to parse using more than a few kilobytes of text using reflection is not going to be fast enough to keep your users happy. If you're on Unity 5.3, you could consider using Unity's built-in JSON utility class. Internally, this is based on Unity's serialization system. It's pretty fast compared to most of the parsers I've tested it against. If you can't do that, consider using a JSON parser that is not based on reflection. Profile it. There are, however, if you can't get rid of this, perhaps you've got an external requirement, you must use an external web service for some reason, there are 3 other strategies you can use to reduce your JSON and XML parsing time. First, don't do it. For some kinds of data, if it doesn't change very often, you could write a system to bake that data down to a binary format that Unity can serialize natively, like a scriptable object or just a standard C# class. When you are loading these out of an asset bundle, for example, that's actually just memcopied directly from storage into memory. That is considerably faster than doing any kind of text parsing, let alone actually trying to figure out what the text says. Granted, there are a lot of cases where this isn't possible. You can't convert that stuff ahead of time, perhaps it's dynamically generated. Instead, try to reduce the amount of work that you have to do at one time. Amortize it. Split your data into small chunks and parse it either across many frames, or, even better, discover the minimum subset of text that you actually need to parse, and parse just that, save the rest for later. Of course, when you do the parsing, save the results, don't do it twice. Of course, there are also some cases where you can't split up the data anymore. You have this giant monolithic chunk of JSON that you must deserialize. It's dynamically generated. It comes from a web service. You cannot change this anymore. What do? I hesitate to recommend this because it's very dangerous, but you could use threads. If you are not careful with your synchronization, you can create race conditions. On some platforms or chipsets, threads are a little bit crashy. But if you know you're running on good devices, if you know you're running on good chipsets, and if you are very careful with your synchronization code, this can be extremely powerful. Remember, of course, the big drawback here, you cannot deserialize any Unity types. You must be deserializing pure C# types, classes and structs decorated with the system.serializable attribute. Another common loading time problem, I hinted at this earlier in the talk, the resources folder. It's really easy to use. People just dump assets into it like it's a truck. It is not a series of tubes, however. However, you can load the assets whenever you want. You load them, you unload them whenever you want. Very convenient, wonderful. However, as the number of files in your assets folder grows and your resources folder grows, the index that Unity calculates for those resources also gets larger. This makes sense. One file, one entry into the index. As that index grows, it takes longer and longer to load up on device. When you start getting to thousands of files or tens of thousands of files in a resources folder, this can take hundreds of milliseconds on a slow device. No one wants to stare at a splash screen for 2 seconds because you were too lazy to remove your temporary assets from the resources folder. Don't do this. If there are things that are in there that are not temporary, they're not debug, you cannot get rid of them, then consider moving them to asset bundles. It's the only way left to you. I'm going to talk about a few things that can speed up your game loading at runtime. Again, most of this can be answered by the profiler. But first, easy win, animator and shader property IDs. A lot of people just call these by strings. I've seen this in many games, professional programmers, first-time programmers alike. Whenever you're calling material set color, get color, whatever, you simply pass in the name of the shader property, just like I highlighted here in red. Well, every time you call that method, Unity is going to hash that string just to get the integer property ID. Every time. Now, hashing a single string, not terribly expensive. How many times are you going to do this in a single frame? More than once, most likely. It is not uncommon to have tens of these in a single frame. It is certainly not uncommon in games with lots of image effects to see 100 or more of these in a single frame. And it's so simple to change. Those integer IDs for the properties are deterministic. It's actually safe to call shader.property.id an animator string to hash at load time. In fact, in a static constructor or in an awake method. Cache them, put them in a static class somewhere, reuse them over and over again. This is free performance. Please stop doing this. Mark talked about boxing already. I am actually fairly famous in the enterprise support community for just yelling boxing whenever I see it in the profiler because it is horrifying. There's no reason to do it. The worst part is that it's actually really easy to do. C# was built on the assumption that you would have a generational garbage collector. Well, we don't have a generational garbage collector in Unity, so all those little temporary allocations are lumped in with everything else, and we have to scan through all of them every time the GC runs. This is terrible for your game's performance. So, you could inspect the raw interface language to try and find the box instruction. Use ILSpy or JetBrains' .peek, both very, very useful. Or pop open something like instruments and search for : box. It will look something like this. If you are looking very closely, in fact, at this slide, those in the front row might be able to see it, that instance of boxing is not happening inside of a coroutine. It is happening directly underneath the runtime invoker. Why is that? Well, it turns out that Unity actually has to call coroutines each frame to find out if they should run. Because of the way we implemented it, it's actually boxing that value every single frame. That's horrifying. Don't worry, though. We actually communicated this to the IL2CPP team, and not only are they aware of it, but it is fixed in 5.3.5 patch 2 or newer. So please upgrade as soon as possible. Get rid of this little uncontrollable piece of boxing. I'm going to go back to talking about strings. People seem to love them for some reason. I don't know why. I prefer numbers myself. But to understand just how string parsing is going to be, let's go over a bunch of different options that you have. Now, when you have any kind of complex string operation, a lot of people like to reach for the biggest, most powerful tool in the drawer, regular expressions. An old quote comes to mind here. Regular expressions, you are not running on a JavaScript runtime. You are not running on a Perl runtime. Regular expressions generate enormous amounts of temporary collections every time you run them to do their computations. This is just internally. What's worse, when I say this allocates a ludicrous amount of memory, that simple string equality comparison there, that's 5 kilobytes of memory for something that could have been replaced with a string equals. You'll notice there are no string lookaheads, there are no collection operators, there's no captures, nothing in there. Nothing fancy. 5 kilobytes. Why do this? Now, some of you are saying, oh, he should have precompiled the regular expression. Yes, I can do that too. It's highlighted on this slide. OK. See the version where I actually capture the regular expression object off and no longer incur that temporary compilation and creation of a regular expression? Yeah, it's still 320 bytes for a straight string comparison. That's not acceptable. Not when you're running on a piece of chewing gum in your pocket. Now, the worst thing is C# string libraries are actually built to be internationalizable. They were built for business applications. So they do a lot of string coercion if you leave them alone. By default, they do culture-sensitive comparison. So this red string match here that I've highlighted on the screen, that will actually return true in the US locale, because in US English, encyclopedia and encyclopedia are apparently the same word. That ligature is the same as an E. In many European languages, that is not true. So one, this can create weird bugs where when someone is running on like a Finnish iPad, it doesn't work, but an English iPad it does. One way that you can solve this, a good way of solving this, is passing in string comparison.ordinal to all of your string operations. This does it the way C and C++ programmers are used to. It actually does a byte comparison. So it simply walks through the string and compares the byte value of each character. Note that it doesn't do any multi-byte conversions there. So that's one instance where you may want to use the culture insensitive comparison instead. However, this is not enough. Some of the string APIs are just slow. One that I've seen trip everybody up is string.startsWith and string.endsWith. Now, I'm going to bet that every single person in this room, I don't care if you've been programming for 5 minutes or 5 years, could write one of these functions in about 10 minutes. It's not difficult. However, if you try string.starts with or string.ends with and you use the culture-sensitive comparison, it is 2 orders of magnitude. It is 100 times slower than the function you've written. Aha, you say. I'm going to use the ordinal comparison. I'm just going to compare the bytes. Yeah, that's still 10 times slower than it should be. If you write your own replacement 10 times faster, please do this. Why, though? It seems strange, right? Well, in order to explain this, we actually have to go a little bit deeper into how C# actually works. Remember, the code you write is a high-level language. It's translated by the C# compiler into intermediate language, IL. And whenever your C# code is invoked by another method, we enter either a call or callvert instruction into the IL. And that just means invoke this method at this other location, or invoke this virtual method, which involves a bunch of lookups. However, method calls in C#, even in C++, not the cheapest thing in the book. You have to create a new stack frame, new execution context, and so on. In order to illustrate this, I'm going to tell you a story about 2 different blocks of code. The code here on my right is the nice, modern C#y version. We have a property with an automatically generated getter and setter. So that's just to show you that there's no funny business. I haven't put anything special into the getter or setter to make them extra slow. And then we just compute the sum of the values in an array. On the left here, I think that's the left. On the left here, we sum the thing up and we store it in a simple plain value type, an integer. So, how many method calls do you see? We're going to count them. 1, we have to get the value from the list. Okay? 2, we have to get the value from that property. Then we actually have to sum up the value that we got from the list and the value that we got from the property, and then we have to set the property again with the computed sum. And then finally, we actually have to call list.count every time we go through this loop. Why? Well, you're accessing a property. That's why. So there are 4. There are 4 method calls. The primitive version, well, there's list.getValue, and everything else is pure arithmetic. You will note that I pulled the list count access out in order to reduce the cost of this loop by 1 method call. How would you expect them to compare? I ran them through 100,000 iterations. The primitive version is 128 milliseconds. This is not something you would want to run in an update loop, but perhaps at initialization time it would be OK. The modern version is 324 milliseconds. It's 3 times as long, and it does the same thing because you used a property. Now, some of you are saying, oh yeah, but you could have made that even faster. Yes, I could have. If I converted this from a list to an array, that actually gets rid of that list accessor as well. And as long as you're not indexing into the array, doing the array arithmetic too many times, that actually cuts that 128 milliseconds down to about 60. So the issue here is that C#, at least as it's run by Unity, does very minimal inlining. Even under IL to CPP, most of the code that our compilers generate does not inline nicely. So even if this is especially true. Remember, any virtual or interface method will not be inlined, no matter what, even if it's just returning a constant. So a call in the source that compiles down to a call in the IL will compile down through IL to CPP or mono into an actual function call in the assembly code. Wonderful. Wait a minute now. Think about something. What about all those nice, convenient properties that Unity gives you, like vector 3.0? Yes, it is calling a method every time you get that, just to get a 0 vector. Every time you call quaternion.identity or vector 3.forward, it is, again, returning effectively a constant. Don't do this. For simple types, make it a const. When you use the const operator, a simple value type will simply be basically pasted into your code as if you had simply entered the value manually. So for most simple things, integers and floats, use a constant. For a more complex type or for very long strings, use a static read-only. I put that caveat in strings in there because, again, if you have a 1 megabyte string and you use it 10 times in your code and you paste that throughout, now your binary has grown by 10 megabytes. Not so good when Apple keeps you down to about 100. Now, trivial method calls. Let's think about these. Quaternion.set. All that does is a little bit of math and sets a variable. Vector 3.scale. 3 multiplications and sets a variable. Why are you incurring the cost of a function call to do this? Transform.translate. It does 1 quick check. Checks to see if you're translating in local space or in world space, and then it actually calls another function. So now you have 8 function calls just to set to basically do some quaternion multiplication and then a method set. Why are you doing this? Don't do these. If you are inside a tight inner loop and you see these things popping up in the profiler, replace all these trivial method calls. Do the inlining yourself and save that little bit of time. Now, please, please, please be professional about this. Profile it before you optimize it. These are micro optimizations. No single one of them will fix a slow game. However, if you see these in an update loop, if you see these in a tight inner loop in an update loop, and you're trying to get from 18 milliseconds and 30 FPS with vsync down to 16 milliseconds and 60 FPS for vsync, this can save you. So when you see it in the profiler, now you know what to do. I want to thank you for listening.